So this is a paper on fast memory-efficient anomaly detection in streaming heterogeneous graphs. It's joint work with Sadek at UIC and my advisor Leman. The method we propose here is called StreamSpot, and essentially what StreamSpot does is it tracks anomalous heterogeneous graph objects as they evolve from a stream of typed edges. So concretely, what happens is, given a stream of typed edges where each edge arrives at a different graph, and each edge has node types and edge types, this gives rise to multiple evolving heterogeneous graphs. And what StreamSpot does is it maintains an anomaly score for each graph on every edge. And there are a number of challenges that we need to handle while doing this. We need to be fast because our input stream is very fast. We also need to be incremental. We can't recompute things while handling the stream. We need to do this in bounded space, even though the stream size is infinite. And of course, we need to be accurate while doing this. So why do we care about this problem? The motivation for us came from a DARPA project where we wanted to do a real-time detection of compromised application software. So we were given this stream of system calls where each event in the stream has a timestamp. It has a subject, which is a process. It has a system called type, which could be the fork, exec, or read or write. And it has an object which could be multiple types. It could be a file, a memory location. And there is a particular ID for every event that tells you which application is triggering this event. And the goal is to detect suspicious applications, intuitively applications that are different from everything else that is growing in the stream at that instant. If you consider every event as a directed edge, each application becomes a heterogeneous graph. And you can then use StreamSpot to assign an anomaly score to each graph. Another potential application is, imagine you have a stream of file system or website navigation traces, where for every navigation event from a source to a destination folder, you have an event. And you have these events for every user. Even in this case, you can view each event as a directed edge, and you have this evolving heterogeneous graph for each user. And you can then use StreamSpot to figure out which users are behaving differently from the others, and they may be malicious. So there is some related work on this domain, mainly on the graph stream clustering and outlier detection. The key difference from us is that we operate on a stream that is one edge at a time. So previous work dealt with one graph, entire graph at a time. And another key difference is that we actually use the types of the nodes and edges in we use it to improve our performance, which was not done before. So in a nutshell, the way StreamSpot is a clustering-based anomaly detection technique. So once we move from data to streaming heterogeneous graphs, we want to maintain a clustering of these graphs online. And we say that the anomaly score of a graph is its distance to the nearest cluster centroid. So if there is a graph that doesn't fit into any of the clusters that we have, that's an anomalous graph. To do this, we need to come up with a way to represent these graphs and compare them that is incremental and that takes constant space. And that's what the rest of this talk is about. So now I'll go into the method details. So for the moment, let's assume that our graphs are not evolving. Let's say we have these big graphs with a timestamp on every edge. Can we come up with a way to represent these graphs in a manner that captures the node and edge types, and that also captures the order of edges in the graph? And the way we propose to do this is by transforming graphs to documents, by constructing a shingle from every node. And the way we do this is we start at a node, we perform a k-hop BFS, and we traverse edges in the order of their timestamps. And this gives us from every node one string. So for an entire graph, you have a bag of strings. And if you store the frequencies of these strings in a vector, you have all your graphs in a common vector space. And then you can compare their similarity using standard similarity measures like cosine similarity. The immediate problem with this is your shingle universe is going to be very large, and it's also unknown in your stream. So is there a way we can represent these graphs compactly in constant space? And it turns out that there is a way to do this called SimHash. And the idea behind SimHash is that given two large high-dimensional documents, in this example D1 and D2, if you pick a random vector in the same dimensional space, if the documents are similar, the probability that they lie on the same side of this random vector is very high. And so SimHash has some nice theoretical results on this. And the probability of two documents lying on the same side of any random vector is actually proportional to their cosine similarity. So what SimHash does is it estimates this this probability by sampling a fixed number of random vectors and counting the number of times that the two documents lie on the same side of the random vector. So concretely, what we can do is, given this document vector, the black vector, we initialize SimHash by sampling L random vectors. You can sample them uniformly from a space of binary random vectors. They don't need to be uniformly at random. You compute a dot product of each of these random vectors with your original document, and you have something called a projection vector. You take the sign of this projection vector to get an L-bit sketch. Once you have your L-bit sketch, you can throw away everything. You can throw away the document vector and the random vectors. And you can use these L-bit sketches to estimate the similarity of two documents. But now let's remember that we have a stream of documents. So you may have new words that get added to documents. And how do we extend SimHash to this case? If we want to extend SimHash to this case, you need to store your random vectors in memory. And then when you have a new shingle or a new word being added to your document, you need to look at the random vector entries that correspond to this shingle and then add those entries to your old projection vector. The problem with this, again, is that the shingle universe is large, but also you don't know the size of your shingle universe beforehand. So you don't know how to actually sample these random vectors in the first place. Is there a way of achieving exactly what SimHash does, but without needing to store these random vectors of this size? And we propose a way to do this called StreamHash. And the key idea is it's simple. Instead of storing these plus or minus 1 values for every shingle, we have a function that computes these values for every shingle. And if we can come up with a way to sample L functions in a way that the values obey the same properties as SimHash, you want the values to be uniformly random and independent of each other, then we can just replace your random vectors with these functions. And it turns out that if you sample your functions from a universal hash family, you get the same properties as what SimHash gave you before. And now you can store these functions in constant space, and you also don't need to know the size of your shingle universe. So now let's go back and look at, if we have a new shingle, how do we update our sketch and projection vectors? And the way we do this is similar to the way SimHash does it. We take our new shingle, we hash it L times, where L is the number of hash functions, and then we get an update vector that we simply add to our projection vector. If we remove a shingle from a document, the procedure is the same, but you just subtract your update vector from your projection vector. And now, this way we have an incremental way to maintain these representations of graphs in constant space. So far we've been talking about documents and shingles, so let's tie this back into graphs and edges. So what we do is, on every new edge, we have a set of shingles that are updated, which is basically a set of shingles that we remove and a set of shingles that we add. Once we have these set of shingles, you can hash these shingles the way we discussed before and update your projection vector and sketch. And the time complexity is, you can do this in constant time. So the dominating factor is the hashing. So you need to do this L times, and then you update your sketch and each element of your sketch and projection vector. Now that you can maintain, so what still dominates is the space complexity. So we need to store the sketch and projection vector of every graph. And the way we work around this is by evicting edges in oldest first order. So this way we always have a constant number of edges in memory, which in turn controls the number of graphs in memory. And now that we can represent and compute the similarity of graphs in a stream, we can go and plug this into a clustering-based anomaly detection framework. So we start off by taking a bunch of training graphs and constructing bootstrap clusters. The centroid of every cluster is what we call the average graph of that cluster. It's simply the average of the shingle vectors in that cluster. This can be computed directly from your projection vectors. On the arrival of every edge, we need to compute the distance of every graph to each cluster centroid. And then we need to update the cluster centroid itself when you add and remove graphs from the cluster. All of this can be done in constant time. And finally, we need to maintain the anomaly score of every graph, which is its distance to the nearest centroid. And this gives us our clustering-based anomaly detection framework. So now I'll move on to the evaluation. In our evaluation, we had three key questions that we wanted to answer. How accurate are we in two dimensions, in two cases? In the offline case, assuming that all our graphs are available offline, and in the online case, how fast can we process each edge? And how does this performance vary as you configure these parameters, such as the sketch size? So I'll first describe the data sets that we use to perform this evaluation. So we construct 5 benign scenarios. Then the way we do this is we automate a user visiting a website and performing a certain activity, such as watching YouTube or visiting CNN. And as we automate this on a host, we collect all the system calls that are running on that host. So this gives us one graph for every benign scenario. By repeating this 100 times, we get 100 graphs. And we have 2 malicious browser-based scenarios in which we automate a user visiting a malicious website, where the malicious website goes and it exploits some vulnerability and gains access to the host. So, and we have 2 malicious browser-based scenarios. Now, given this, assume that all our graphs are present offline. If we split this, you split up your graphs into a train and test set, construct your bootstrap clustering, and then score the test graphs based on their anomaly score. How do we perform? We compare this to isolation forest, which is an ensemble-based anomaly detection technique. And we feed isolation forest with graph structural features. And these features we engineered them by talking to security experts who told us that, okay, in malicious graphs, they tend to have a larger diameter. So the features come from domain experts. And we looked at the precision recall curves for StreamSpot versus isolation forest. And what we saw is that isolation forest tended to rank malicious graphs low, which for a given recall, it ended up in a lower precision compared to StreamSpot. So now we move on to the online evaluation for which StreamSpot was designed. And what we do is we stream in every edge of a test graph, one edge at a time. We also control the number of test graphs that are growing simultaneously in the system. So you can imagine we pick 50 graphs at random, we grow them until they finish, and then pick the next 50 graphs and grow them until they finish. And on every edge, we have the anomaly scores of every graph that we've seen. So we can compute the average precision, which is the area under the precision recall curve. And that gives us the following metrics for our online evaluation. So on these plots, the x-axis is the edges that we've seen so far, and the y-axis is the specific metric that we're looking at. So let's first look at the average precision. You can see that the interesting thing to note is that you have these periodic dips in performance. And those dips happen at precisely the time when your new batch of 50 graphs is just starting to grow. And this is because when your graphs are just starting to grow, you don't have enough information to cluster them accurately. So you have a dip in performance. But it recovers fairly quickly. And if you look at the same performance as we vary the sketch size, you can drop to fairly low sketch sizes without having a big hit in your performance. And there are 2 reasons why you'd want to reduce the sketch size. One is to save memory. The other is your per edge running time significantly increases when you use smaller sketch sizes. And next, we look at how does the performance vary. Remember I mentioned that we evict edges in oldest first order and then store a fixed number of edges in memory. So what we do here is instead of evolving 50 graphs at a time, we evolve 100 graphs at a time so that when we evict edges, we actually evict them from graphs that are actively growing, not graphs that are finished growing. And we can see that performance, even in this case, is not affected too badly. And if you look at the actual memory usage, let's say that I store only 15% of my stream, I can actually perform my entire computation using just 75 megabytes of memory. And finally, when I look at the per edge running time for different sketch sizes, for a sketch size of 1,000 bits, we're able to process every edge in less than 70 microseconds. So we can scale up to 10,000 edges per second. If we go down to 100 bits per sketch, you get a processing time of over 100,000 edges per second. And this way, we can actually scale to a real stream of system calls on a host. So to summarize, we started off with data that was an event stream that we considered as evolving heterogeneous graphs. We came up with a way to represent these graphs in bounded space and to incrementally maintain these representations. And then we plugged this into a clustering-based anomaly detection framework, which we were able to show that is accurate, fast, it's fully incremental, and it consumes bounded space. So our code and data are available at the following website. And I'll just conclude by thanking the following agencies for supporting our research. Thanks.
Any questions from the audience?
So the very first step, converting data to a streaming heterogeneous graph, is that a standard process that you're leveraging, or is that something that was developed for this?
The way we're doing this is application specific. And the goals were to capture the edge order and to capture the types of different nodes. And you want to do this in a way that you have some kind of fuzzy similarity between multiple graphs.
Okay. And is that described more in at that website?
Yeah, in the paper, yes.
Okay, thanks.
Two questions. Hi.
Hi, yes.
So the first question, I think it probably doesn't matter for your use case, but did you think about a way to delete edges graph? Because your graphs always grow when you're using a hash, like a hash sketch, so there's no problem increasing the graph.
Yes.
But have you looked at, I mean, is there a way to, what if my graph can also delete edges?
It works even for deletion of edges. So when you add an edge, you're basically adding and removing. You're removing the old shingles and adding the new shingles. When you delete an edge, you're doing the same operations. So the representation that we propose, it can be applied directly to edge deletion.
All right, thank you. Second question. So in your experimental data sets, you have basically a browser and everything else. Like, have you tried, for example, if one of the benign data set, for example, compiling a kernel while also browsing the internet, how does this affect your anomaly detection? Because your ROC curves are super great, but it's basically just a browser versus anything that's not a browser. So it seems to me.
So in the scenarios that we constructed, we traced all the system calls on the host, including system calls from processes that are not the browser.
Yeah, but there was no activity by the user except browser, right?
There was no activity by the user, except for the browser. Yes.
All right, so it might be worth be looking into, like curve compiling or something else.
Yes.
All right, thank you.
Thank you.
Yeah, in the same vein, a very interesting presentation. Thanks, Emaad. But did you try to characterize how consistent your benign graphs have to be? Like so if there's an element of stochasticity, like the other guy just said, it could be interesting if I'm compiling code and also browsing the web. But in that same vein, like, did you try to characterize how consistent they are? Because they must have some sort of non-anomalous behavior that you're keying on.
Yeah, this is an important assumption that, which is true. Benign data is cheap for us to collect. So if you're deploying this in an enterprise, You can trace the activity of all your users and just trace everything that they're doing. And this gives you your benign graphs. We haven't characterized how good these need to be, but we know that they need to be pretty good in order to catch anomalies.
Thanks.
Hi. So your edges are coming as streams, right? But when you construct the shingles, if I understand correctly, this is a collection of edges that are local to each other. But if you already hash the graph, then each incoming edge, how can you construct the shingle?
So the edges don't have to be local. So the edges they arrive on the graph, they can arrive anywhere. For every edge that arrives, you need to construct the shingles that it's replacing. And so the details are in the paper. You basically look at what are the affected nodes, and you perform an.
But that means you need to do some traversal locally, right, surrounding that edge.
You need
but that information might not be there if you already hash the graph.
We still store the graph in memory, but we evict edges in oldest first order. So part of the graph is still there in memory for shingle construction.
Okay, thanks.
Okay, great. Thanks a lot.
Thank you.